Force on moving charges in magnetic field. So the topic is called force on moving charges in magnetic field. This is the topic. So first thing that I want to tell you, we are not concerned in this topic who is creating magnetic field. We are not concerned in this topic as to who is creating magnetic field. Okay, anybody can create magnetic field, anybody, that we are not concerned. For some time we will assume magnetic field to be uniform and steady. For some time we assume magnetic field, whoever is creating the magnetic field, that magnetic field to be uniform and steady. We will assume it to be uniform and steady. So what does it mean by a magnetic field is uniform? What does it mean by a magnetic field is steady? So uniform means it has same magnitude and direction at all points in space. That is the meaning of uniform. Okay, even in schools we have uniform, means same colored dress for all students. So whichever student you pick from that school, he has the same colored dress. That is uniform. Similarly, the magnetic field has same magnitude and direction at all points in space. That is what we mean by uniform. And steady means magnetic field does not change with time. So steady implies magnetic field, that is B, is not changing with time. That is the meaning of steady. You can have a magnetic field which is uniform but not steady, and which is non-uniform but steady. So let's look at that. I can have a magnetic field which is uniform but unsteady. This is possible. You can have such a magnetic field. I can also have a magnetic field which is non-uniform but steady. Let's look at example. When I say uniform but unsteady, let us look at an example. Suppose in certain location, in a room, let us say, the magnetic field is pointing in that direction and it is 4 Tesla. Today it is 4 Tesla, but everywhere in the room it has same value, same direction. So wherever you go in the room, it has same magnitude and direction, so you say it is uniform. Okay, but suddenly tomorrow in the same room the magnetic field became 5 Tesla. So the magnetic field became 5 Tesla, but it is again same everywhere. Wherever you go, it has same direction, same magnitude, but it is changing with time. Today when you look at it, it has some value. Tomorrow when you look at it, it has a different value. So this is a case of uniform. It is taking same value everywhere, but unsteady. It is changing with time, but maintaining its uniformity. Then you have the other case where it is non-uniform but steady. That means if you take a room, magnetic field here is 4 Tesla in certain direction, here is 5 Tesla in certain direction, here it is 6 Tesla in certain direction, here it is 7 Tesla in certain direction. So everywhere it is in the room, everywhere it is different. So it is non-uniform. But you come tomorrow also, these values are there like this only. You come after 1 year also, these values are like this only. So let's say these values are not are same today, tomorrow, and so on. They are not changing. So this is a case of non-uniform because it is changing from place to place, but it is not changing with time but steady. So steadiness is related to time, uniformity is related to space. Space and time are the two important things when we are dealing with the material world. Space and time. So that is the idea behind this. Now, for certain time, we will assume the magnetic field, whoever is creating the magnetic field, that magnetic field to be both uniform and steady. We'll assume that, and we will do our discussion. As we go ahead in our discussion, there will come a time when we will also take non-uniform fields, and at a later stage we will also take unsteady magnetic fields. Okay, now the topic which we are doing is force on moving charges in magnetic field. That is the topic, force on moving charge in magnetic field. Now let us come back to that. So first there are some laws of nature which we will study in great depth. So our topic right now is force on moving charges in magnetic field. This is our topic, force on moving charge in magnetic field. So it's a magnetic field. First important point is a magnetic field does not exert force on stationary charges. Does not exert force on stationary charge. This is a very important point. Electric field exerts force on stationary charges. Electric field exerts force on stationary charges. That we know. For example, if a charge is stationary, then QE is the force on it, where E is the electric field. So we know this. Q into E is the force on a charge Q when placed in electric field E. But magnetic field does not exert force on stationary charge. That's a very important point. So that is how nature works. Not only that, if you throw a charge along or opposite to magnetic field, along or opposite to magnetic field direction, again there is no force on the charge due to magnetic field. Again there is no force on charge due to magnetic field. That means, suppose if I have magnetic field to the right in certain room and I am throwing a charge to the right, this does not experience force because the velocity is parallel to magnetic field. Then no force is experienced by charge in magnetic field. Similarly, if I throw another charge let us say to the left, so here the velocity is anti-parallel to magnetic field. I use the term anti-parallel, it is parallel only but in opposite direction. Again no force. So the thing is, when you throw a charge along magnetic field or opposite to magnetic field, no force. Why it is like this? We will understand this, but this is how nature works. This is the law of nature. So I can say these are laws of nature. So one thing I must tell you, the whole of electromagnetism topic It is an experimental topic. So first there were lots of scientists who performed experiments, and then they came to conclusions how nature is working. Then they formulated the laws. So the law is formulated after seeing how nature is working. So we must keep that in mind. Now let me go to the core concept in this topic, which is a very important concept. The core concept is as follows: the force, the law governing the force experienced by moving charge in magnetic field. I directly want to write it. So the law governing the force experienced by moving charge in magnetic field is F equal to Q V cross B. This is the law. Okay. So right now you can even relax the restriction that magnetic field is uniform and steady, because we are looking at force at that moment. So whatever is the magnetic field value at that moment, you can take and calculate, no problem. So I am relaxing here for a minute the condition that magnetic field is uniform and steady. It need not be, still the law works. But this is the law governing the force experienced by moving charge in magnetic field. Let's explore this law in detail. Let's explore this in detail, because the whole topic revolves around this only. If you understand this thoroughly, 80% of job is done. So let's come back to this law. F equal to Q V cross B. So you see, first point that I am going to tell you, obviously if V is 0, force is 0. You can see it from the law. Okay, you can see it from the law. That is, magnetic field does not exert force on stationary charge. No force on stationary charge. Okay, no force on stationary charge. Now one more thing, if V is parallel to B, you can see from the law that V cross B, the angle between V and B is 0. So V cross B will be VB sine 0, which will be 0. So again no force. Similarly, V is anti-parallel to B. I write it like that. This is my symbol for writing anti-parallel, means they are in opposite directions. Okay, my symbol, it's not a standard symbol. My symbol for saying two quantities, two vector quantities, okay, two vector quantities are at 180 degrees to each other, are at 180 degrees to each other. Even in that case, what will happen to cross product? V cross B will become, let me take only the magnitude, I am looking only at the magnitude right now, is VB sine 180 degrees, so which becomes 0. So you see, all the conclusions which we first stated are coming from this law. So this law is very important. It will tell you many more things also, much more than what we have written here. It will tell you many more things than what we have written here, much more than what we have written here. So let us go deep into this and explore this. So F equal to Q into V cross B. We should never forget this law. Now I am getting force by doing cross product of two quantities, which is velocity and magnetic field. I am getting force by doing cross product of V comma B. When you do cross product, the vector that you get is perpendicular to both original vectors. So this means the vector that you are getting, the force, is perpendicular to velocity also, and force is perpendicular to magnetic field also. This is the idea of cross product. When you cross two vectors, the answer that you get, it is perpendicular to both original vectors. So the answer which we are getting is F here. It is perpendicular to V also, it is perpendicular to B also. F perpendicular to V is a very important thing in this topic. This means if F is perpendicular to V, this means F dot V is 0 because dot product of two perpendicular vectors is 0. Okay, already here I am saying power of magnetic force on moving charge is 0 because F dot V gives you power of magnetic force on moving charge is 0. F dot V is power, instantaneous power. Okay, let's go further. You can write this as F dot velocity is ds by dt, rate of change of displacement is 0. So I can immediately conclude F dot ds is 0, which implies, if I go to next page, integral F dot ds is 0. If F dot ds is always 0, when you integrate, add up all zeros, you get again 0. Implies work done by magnetic force on moving charge is 0. Work done by magnetic force on moving charge is 0. So this is a very, very important point. Magnetic force never does work on moving charges. Very important point. Magnetic force never does work on moving charges. That's a very important point. It never does work. If this is the only force acting on the particle, if magnetic force is the only force, no other forces are acting. If magnetic force is the only force acting on particle, if magnetic force is the only force acting on particle, then by work energy theorem, we can write work done by magnetic force is change in kinetic energy because there is no other force acting except magnetic force. But magnetic force does 0 work, which implies change in kinetic energy is 0, which implies kinetic energy is constant, which implies speed of particle is constant. So you see how many conclusions are coming from here. Just one law, but it is going very, very deep. It is actually exploring the whole of mechanics. This electromagnetic law is exploring the whole of mechanics in different ways. So this has a relation to great amount of mechanics, this law. We will see down the line very complex things like coupled differential equations when we are solving the motion of a particle and how to decouple them and how to solve them. All complex things are going to pop up. So if I put everything at one shot, you are getting magnetic force perpendicular to velocity. So F dot V is 0. So F dot ds is 0. So work done by magnetic force is 0. So magnetic force cannot change kinetic energy of particle. That means magnetic force cannot change speed of particle. All, if I put it in the next page, once again look, F is q v cross b implies F perpendicular to V, first important point, implies F dot V equal to 0, second important point, implies F dot ds is 0, third important point, implies work done by magnetic force on moving charge is always 0, fourth important point, implies magnetic force cannot change kinetic energy by work energy theorem. Magnetic force cannot change kinetic energy of charge. Magnetic force cannot change the kinetic energy. Implies magnetic force cannot change speed of charge. So this is the conclusion. So at best, what it can do? At best, magnetic force can change direction of charge. That is the best it can do. It cannot change speed, but it can change velocity by changing direction. At best, magnetic force can change direction of charge motion. That is what it can do. That is what it will do in most of the cases. That is the use of magnetic field. It's a great use. There is a device called cyclotron where this fact will be very useful for us, that magnetic force can change direction of charge's motion, but it can't change the speed. Okay, it can't change the speed. So magnetic force doesn't do work on moving charges. There are some cases where it might appear to you that it is doing work, but it doesn't do. Okay, if you go deeper into those scenarios, you will see something else is at play there, which is doing work, not magnetic force. Magnetic force never does work on moving charges. So that is the starting point of this topic. Now, having reached till here, now let us look at what are the possibilities, what are the possible paths taken by a moving charge in magnetic field. So we will consider now uniform and steady magnetic field. What is the path? What is the path followed by a moving charge in uniform plus steady magnetic field? What is the path followed by a moving charge in uniform plus steady magnetic field? This is our discussion. So there are only three possibilities here. There are only three possibilities. First one is a straight line. So a charge moving in magnetic field can go in a straight line, that's possible. The magnetic field must be uniform and steady. This is a very important restriction. If you make it non-uniform, many more paths are possible than what I am outlining here. If you make it unsteady, again many more paths are possible than what I am outlining here. Second, you can have a circular path, that's possible. And third, what we call as a helical path. What is it's called helix. How does it look? Basically like coils of a spring, so the motion is exactly like this. That's helix. So if the charge moves along the coils of a spring, that is helical. So same as spring coil. So these are the only three possibilities for a charge moving in a uniform and steady magnetic field. So we will now go into each of these motions. First one is straightforward, second is slightly complex. First plus second, if you understand, you can understand third by using a certain concept. So this is the topic about. The whole topic is this only. Okay. Later we will look at non-uniform magnetic fields and how to find out the path taken by the charge in non-uniform magnetic field. We won't do cases where there is a time varying magnetic field as of now. When the situation demands, we will look at them. So this is the scope of the whole topic. Now let's go to the motion of this charge moving in a uniform and steady straight line. So I am discussing each of these cases when they are possible. Straight line, we know, see, if the magnetic field is pointing to the right, if I take a charge and throw it to the right, now here V is parallel to B, which means V cross B is 0. So force which is given by Q V cross B is 0. Force on charge is 0. Implies acceleration of the charge is 0. Implies velocity is constant. Means neither the direction nor the magnitude changes. So the charge continues with same velocity. So path is straight line. Implies path is straight line. Same thing goes if I throw the charge opposite to magnetic field also, same thing works. Again V cross B is 0. So Q into V cross B is 0. So force on charge is 0, which implies acceleration is 0, which implies velocity is constant, which implies direction will not change, neither magnitude will change of velocity, which implies straight line path. So when the charge goes in a straight line, when the velocity is parallel to magnetic field, or when it is uh, anti-parallel to magnetic field. So straight line, the angle between velocity and magnetic field should be either 0 radians or pi radians, one of these two cases. Then it is a straight line path. Straightforward argument. Now let us come to circular path, which is very complex. You have to understand this in detail. So let's come to circular path. Straight line path is done. Circle. Circular path in uniform plus steady magnetic field. So this is a case where the angle between velocity and magnetic field to start with is pi by 2, and that angle will be preserved throughout the motion. If the starting angle between velocity and magnetic field is pi by 2, okay, that angle will be preserved throughout the motion. It will continue to remain pi by 2 only. So this is a case of a circular path. Now how do we analyze this? How do we know it is circle? I will prove later with mathematical analysis that it is a circular path. We will do a quantitative analysis later. Quantitative means mathematical. So now I will go into qualitative analysis, which means a theoretical discussion and trying to show you that it is a circular path. So for this, what we will do, suppose I take magnetic field into the board. Now because we are working with 3D, I will use this notation. Into, if I put with a circle, that means it is into whichever vector quantity I show with this cross and circle, that's going into board, and whichever vector quantity I show with the circle and dot, it is coming out of board, out of the board. Okay, so this magnetic field right now is going into the board. Okay, so one direction I have taken care by showing this symbol. So remaining directions are on the plane of this page, which I can draw. So to make my drawing comfortable, I am doing this. So right now magnetic field is into the board. Let us say I have a positive charge here, Q. Let's for now put the restriction that it is positive. Now I am giving velocity to this on the plane of this board. Okay, so the velocity is on this screen, any direction. I can show some direction, maybe this direction. So I have thrown it in that direction. Velocity is on the screen, whereas magnetic field is perpendicular to the screen. So the angle between velocity and magnetic field is pi by 2, because any line on the screen makes 90 degrees with the line perpendicular to screen. Okay, so angle between velocity and magnetic field is pi by 2. Now at this instant, what will be the force direction and force magnitude? We know that force is given by Q into V cross B. First let us look at the magnitude. Angle between V and B is pi by 2. We just now saw that. So Q into VB sin pi by 2 is 1. This is the magnitude of force. And what about direction? Let us do V cross B. Now you have to do cross product. Now this is where I suggest you follow the procedure which I am about to say for finding cross product. Best procedure. Whenever you have two vectors to be crossed, first you join the vectors by tails. Sometimes you have to imagine it if it is 3D. Imagine joining the vectors by tails. Then form a plane containing both the vectors. Please understand this very carefully. Form a plane containing both the vectors. Take a screwdriver or a screw, keep it perpendicular to that plane at the point where tails are joined. Keep it perpendicular to plane at the point where tails are joined, and rotate from first vector to second vector by smaller angle. Rotate the screw from first vector to second vector by smaller angle. See how screw moves. That is direction of V cross B. So what are the steps? Steps to find cross product. Okay, at this stage it is futile to discuss steps to find cross product because this is the first topic that we have done in our course. But anyway, still, so steps to find cross product. of two vectors A and B. Okay, so this is very very important what I am about to say. If you master this, you can tell the direction without following any hand rules or anything. Just by observation, visualization, you can tell this, because visualization is very key for a physicist. So step to find cross product of two vectors A and B. Suppose I want to find direction of A cross B. Steps to find direction of cross product. I'll be more precise. Direction of cross product of two vectors A and B. Suppose I want to find direction of A cross B. So step 1 is join A and B by tails, or visualize. Join A and B by tails. Do it mentally. Okay. Do it mentally. Form a plane containing A and B. There will be one unique plane which will be containing both these vectors A and B. Okay. Then 3. Put a screw perpendicular to plane. Put a screw perpendicular to plane at point where tails of A and B are joined. Tails of A comma B are joined. You have to visualize this. All this you have to visualize. It will take some practice. After that, it will be very fast. The advantage of this is you will not be using some Fleming's left hand rule or some right hand rule. You need not use that, and it is best. This is the best method, because in exam, if you start using the Fleming's left hand rule or right hand rule, you have to bend and twist your hand in varieties of ways, and you might as well fracture it. So I am not suggesting that. Or you will be doing some Kathakali or Bharatanatyam dance in the exam hall, putting your hand this way and that way, which I do not want. So you master this method. So put a screw perpendicular to plane at point where tails of A and B are joined. Now fourth step is rotate screw from A to B by smaller angle. That is very important, by smaller angle. And see how screw moves. So final step, direction of motion of screw. Direction of motion of screw is direction of A cross B. Is direction of A cross B. So this is the steps which we will follow. Okay, now look at this thing here. I want to do V cross B. V cross B. And I have taken a positive charge. I want to find direction of V cross B. So V is on the board, B is into the board. Visualize these two as joined by tails. I have shown V as a blue vector. Imagine magnetic field as a red vector starting from the charge and going into the board. A red vector. Imagine. Visualize. Form a plane containing these vectors. So I formed a plane. Put a screw perpendicular to plane at the point where tails are joined. Rotate from V to B by smaller angle. If you rotate the screw, I can see its direction as this. That is the direction of V cross B. V cross B direction. Okay. If you want to use some right hand rule, you can, but again you have to twist your hand. It's not easy in some cases. This is the best which I am saying. V cross B, you have to visualize. First you form a plane, put a screw perpendicular to plane, rotate from V to B by smaller angle, see how the screw moves. You get that direction. Okay, so you got V cross B in that direction. So you see V cross B is perpendicular to V as we have expected. It has to be. Cross product gives you a vector which is perpendicular to both the vectors, both the original vectors. Okay, V cross B is also perpendicular to B, but that is not very useful for us. But V cross B perpendicular to V is a very useful quantity. So you are exerting a force perpendicular to velocity. So if you go back, Suppose I have a block. If I have velocity in this direction, if I apply force in the same direction, of course speed increases, direction will not change. If I apply force in opposite direction, speed decreases, speed decreases, direction right now will not change, maybe over a period of time it might reverse direction. Instantaneously direction remains same. Suppose force makes acute angle with velocity, then speed increases and direction also changes. Why? Because force has a component along velocity, so speed increases, direction anyway changes. If force is opposite to velocity, I mean force which is making obtuse angle with velocity, speed decreases because force has a component opposite to velocity and direction also changes. Now the case is when force is perpendicular to velocity, this is a very interesting case. As of now, force has neither a component along velocity nor a component opposite to velocity. So it neither can increase speed nor decrease speed. It can only change direction. So it will, let us say, change the direction, and this block, let us say, turned a bit like that. Now after turning a bit, we have a new question with us. Now velocity has changed direction. Now is the force same as in previous case, or did it also change direction? If the force is same as previous case, it is still acting up. Now in the new scenario, force has a component along velocity, so speed will increase. But suppose force is also intelligent and force also changes direction, it is again perpendicular to velocity, means now force is acting in that direction. It is again perpendicular to velocity, so it will again turn velocity. Again force is also changing direction. So force is changing direction continuously, velocity is changing direction continuously, so that both are always perpendicular. Then one of the possibilities is it will go in a circle. Okay, of course if the force has constant magnitude, it's a circle only, no doubt about that. But force can have varying magnitude. In this case it is a constant magnitude force, so it can go in a circle. So force always perpendicular to velocity. Look at this, force perpendicular to velocity always, not at one moment. And if magnitude of force is constant, then path is circle. Okay, I am assuming no other force is acting except this force. So this is the case where particle goes in a circle, and that's exactly the case which we are encountering in our discussion here. So right now the force is perpendicular to velocity, so it cannot change the magnitude of velocity. Why? Because force neither has a component along velocity nor has a component opposite to velocity. It will change direction. So the charge will slightly take a turn like that. It will turn like that. Okay. After turning, now what is the direction of new velocity? The direction of new velocity is that. Okay. Again when you calculate force V cross B, it will again be perpendicular to velocity like that. So it will again turn it. So it's ultimately trying to take it in a circular path. That's how you get to a circle. And magnitude of the force, okay, magnitude of the force is always this only. It is not changing. Why it is not changing? Charge does not change. Speed is not changing because magnetic field cannot change the speed. Magnetic field value is same because I took a uniform and steady magnetic field. So it's a constant magnitude force, but always arranging itself perpendicular to velocity, so the path will be a circle. So this magnetic force is acting towards center, trying to move it in a circle. So this is the case where here magnetic force is acting towards center of circle. So this is the case of a circular path. So this must be clear. Now let's do some mathematical calculations here. Can I find radius of the path if I know the speed with which I am throwing and the magnetic field value, and of course charge is given? Can I know the speed? Can I know the radius of the circular path? So that's the question which we are asking. So when angle between velocity and magnetic field is pi by 2, I said path is circle, can I find radius of circle if Q, V, B and mass of the charge are given? Can I find it? Simple. Apply F equal to ma for this charge. Apply F equal to ma in radial direction, means towards center. In radial direction, towards center of circle. You apply this in radial direction. So force is QVB sine 90. That is the force, magnetic force towards center. QV cross B. This force I must equate to mass into acceleration in circular motion. We proved it long back to be V square by R. So F equal to ma I have applied. Here this is the acceleration. Force acting on this charge towards center, which is magnetic force, is mass into acceleration. So from here, radius of the path comes out to be mv by qb. This is a very important formula. You can remember it, but the idea behind the derivation is important. F equal to ma in radial direction. So quite an important result. Not only that, there are some more things here which we must explore, and there can be very tricky questions in this case. Please note, magnetic force is a constant magnitude force. Magnitude of force is constant, but force direction is changing. It is always pointing towards center, but force direction changes. For example, you take this charge going in a circular path. When the charge was here, force was acting this way towards center. Let us say that is west direction. If I say these directions are east, west, north, south. So right now force is acting in west direction. Same charge, when it comes to the top, force acts towards center, but no, it is in the southern direction. So the direction of force is changing. Same charge, if it comes to this point, force is acting in eastern direction. So force direction is changing, which means this force is a not constant force. This force is not constant, because in circular motion force is not constant in direction at least. So this acceleration, please note, is not constant acceleration. It's a constant magnitude acceleration, but not constant acceleration. So many people wrongly apply V equal to U plus AT, S equal to UT plus half AT square, etc. in these cases, which is extremely incorrect, which is not at all acceptable, which means you have not understood circular motion. Anyway, so this R equal to mv by qb is a very important thing. Now let's take this formula, R equal to mv by qb. R is of course the radius of circular path. So this is radius of circular path. If you want, you can write this mv as magnitude of momentum of charge. Magnitude of momentum of charge, which means you can write it as R is P by QB. Generally we use the symbol P for momentum. I am just only writing the magnitude of momentum. We are not concerned with direction. Direction of momentum is changing continuously because velocity is changing in direction. Now what about omega, angular speed in this circular path? Omega is V by R. So from the above relation, V by R happens to be QB by M. Now I want to tell you something very important here related to omega. Omega of charge is always same irrespective of the magnitude of velocity with which charge is thrown. With which charge is thrown. This is a very important thing. Let me help you understand this in a better way. Let me take an example. Suppose I have a magnetic field into the board. In the first case, I take a charge, first experiment, and throw it like this with a velocity v. Okay. What is the angle between velocity and magnetic field? Velocity is on the plane of white board, magnetic field is into the plane of white board, so angle is 90 degrees. So we are falling into the circles case. So V cross B, if I do it by visualization, it will point in this direction. That is the direction of force. and that is also the direction of center. So you can mark the center if you calculate the direction of force. That is the starting point in any problem. First you find force on the charge, knowing that it goes in circular path if V is perpendicular to B. The direction of force also tells you direction of center. So this charge is going in a circle with that center, something like that. Something like that. Now, suddenly, if I reduce this velocity to a lesser value, which I am showing with a red color, the force will be less. Now it will go in a smaller circle. Okay. Center will be along that line only. Suppose the center is, let us say now here for this red circle, it will go in this path and come back. Surprising thing is, time taken for one round of violet circle and time taken for one round of red circle is same. So time taken for one round of violet circle and one round of red circle is same. Why? This is what you should understand. What is omega qb by m in both cases? Is it dependent on the velocity? In first case, in the violet circle case, velocity was more. In the red circle case, velocity is less. But omega does not feature velocity at all. Okay. For example, violet radius is mv more by qb. So omega will be v more by r for violet, which is more, that is qb by m. Similarly, omega for the second case will be v less by r less, or r for red, which is again qb by m only. In both cases, the omega is coming out to be same. If omega is same, if angular speed is same, both will take same time to cover 2 pi radians angle, because angular speed is same. Okay, so by the time the violet circle is completed, the red circle is also completed in same time. Or you can argue like this: in the violet colored case, speed is more and it is going a greater distance, but time is same. In the red colored case, speed is less and it is also going lesser distance, lesser perimeter of circle, so time is same. So time in both cases is same because omega is same. In fact, time period, time for one circle completion is 2 pi by omega. Okay, so you can write it as 2 pi m by qb. 2 pi m by qb. This is a very important point, very important thing in our discussion. Very, very important thing, very crucial thing. Okay, so that's what I mean by omega is same. Now let us put all this discussion into practice by doing a couple of examples. So first example which I am going to do is as follows. I have got a boundary separating a region of magnetic field with a no region of magnetic field. So the upper part contains magnetic field, which is of course uniform and steady. So unless I specify it, we take magnetic field to be uniform and steady from now on. And the lower region has no magnetic field. So this red line is the boundary separating the upper region and the lower region. Now, one more thing I want to tell you before I go to this example, just one small thing. Force is given by q v cross b, right? Q v cross b. V cross b is giving direction of force, but that is only for positive charge. Please note this. I have been taking positive charge here. So direction of force is along v cross b for positive charge. See, I took here positive. If it is negative charge, you must reverse the direction of v cross b. Force will be opposite to v cross b for negative charges. Keep that in mind. Force is along v cross b for positive charge. Force is opposite to v cross b for negative charge. Okay. So now here I have this idea. First I take a positive charge q and I am throwing it with a velocity v like this. This angle is given to be theta. In another experiment, I am throwing a negative charge with same velocity v, let's say minus q, and an angle theta only. This is one experiment. The red colored experiment is one experiment, and the separate experiment is that violet colored experiment. In one case I am throwing positive charge with same velocity at same angle theta to the boundary. In another case I am throwing a negative charge with velocity v at same angle theta to the boundary. Okay, this is experiment 1. So I call this experiment 1, and I call the other one experiment 2. Question is, find the time spent by the charges in magnetic field in both experiments. Find the time spent by charges. Find the time spent by charges in region of magnetic field. In the region of magnetic field in both experiments. This is the question. So in one experiment I have got a positive charge thrown with velocity v in certain direction. Okay, and the magnetic field is not in the whole space. It is in the upper half of this dotted line, but in the lower half there is no magnetic field. The magnetic field which I am taking is of course uniform plus steady going into the board. Okay, to be more clear I am mentioning it. So we have to find this. First let us understand this question. What is the angle between velocity and magnetic field? Without thinking, some people will say theta. They are wrong. I am asking angle between velocity and magnetic field, not velocity and some boundary. Please understand. Velocity is on the board in both cases. Magnetic field is into the board, so angle is 90. So in both cases velocity and magnetic field are perpendicular to each other. So this goes into the case of a circular motion. Okay, what is theta? Theta is something different. Theta is angle between the velocity at the moment of throw and the boundary, not magnetic field. Boundary, there is some boundary which I am showing by red line. So be careful. Now first let us look at this red colored charge motion in great detail in the next page. So this is the boundary. The charge is thrown with a velocity v at an angle theta. Magnetic field is into the board. It's a positive charge. So let us find v cross b. V cross b is in this direction shown along the dotted line. So center must be somewhere there. Okay. With that center we will try to draw a circle. So something like this. And it will, after hitting this boundary again, it comes out where there is no magnetic field. Once there is no magnetic field, it starts going in a straight line. Okay. Now this is the center of the circle. I will join this point also to center. So velocity is tangent to the circular path, means it is perpendicular to radius. Immediately I can say this angle is also theta. Check for yourself, because this is 90. This has to be 90 minus theta, so that has to be theta. Same way this also has to be theta, symmetric scenario. Okay, symmetric scenario. Symmetry is there. Now what is the omega of this charge? Omega is qb by m. It is not dependent on the speed with which you are throwing the charge. And what is the angle subtended by this circular arc at center? Be careful. Angle subtended by circular arc is this. In radians, if I say, it is 2 pi minus 2 theta. So the charge is going by this angle with this angular speed qb by m. So time spent in magnetic field is angle divided by angular speed. I can do this because angular speed is constant. So it becomes 2 into pi minus theta into m by qb. That is the time spent by this charge in magnetic field, positive charge. You can also do it in another way. Time spent is arc length that it is traveling, the charge is traveling, by speed. What is arc length? Radius into angle subtended, which is 2 pi minus 2 theta, by speed. But we know radius is mv by qb. Okay, I am substituting radius as mv by qb. The v gets cancelled and you are ultimately getting this same value. So even if you do like this, which is a long method, you are getting the same value. So time is this arc length by the speed with which, constant speed with which it is going. Speed is constant because magnetic field never changes speed. It can only change direction of the velocity. So we got 2 into pi minus theta into m by qb as the time. What if it is a negative charge? Now let's go to that case, which is the purple colored case. So this is the region. Let me draw it in a better way. So this is the region. Okay, no matter how much I try, I think I am not doing justice. Okay, let me do it like this. So charge is now negative charge. Please note this is very important. Thrown with same velocity v at an angle theta. Magnetic field is into the board, uniform and steady, of course. Now v cross b is of course in this direction, but because it's a negative charge, force is opposite to v cross b, means it should be in this direction. It should be in that direction. So center must be somewhere here. I call this as center. Now this is the difference. So with that center, I will try to complete the circle. It will come out to be something like that. Let me do a better justice to this. Okay, I will take the center to be somewhere here. It's better so that the diagram looks good. Okay, so this is the center. So now if I drop a perpendicular, this angle is theta. By symmetry, this angle is also theta. So the charge subtends 2 theta, the arc subtends 2 theta at center. So time spent here is angle subtended at center by angular speed. This is the time. This is the time spent by this negative charge in magnetic field. Or you can also say time is arc length by speed, the long method. Arc length is radius into angle at center by speed, and radius we know is mv by qb in the case of charge moving in magnetic field in circular path. The v gets cancelled, so you have 2 theta m by qb. Okay, the same result that you got there, I am getting here also. If you see, the time spent by the positive charge and negative charge are different. Positive charge is spending this much time, 2 pi minus theta m by qb, whereas this is spending 2 theta m by qb. Both are different, so you should be very careful. So what is it that I want to bring out of this? V cross b gives direction of force for positive charge, minus v cross b gives direction of force for negative charge. Because q v cross b, if q is negative, there will be a minus sign which is coming up in q. So minus v cross b gives direction of force for negative charge. This is the important thing. This is one of the examples. Let us look at another example in circular path. Very interesting example. So I have a region containing magnetic field. Magnetic field is only in this region. Let us say it is going into the board. Okay. So only within those parallel lines magnetic field is there. Of course, it is a uniform and steady magnetic field. Uniform and steady magnetic field. Now suppose this region's width is, let us say, d, and here I have a positive charge of value q. It is thrown like this with a velocity, let us say, v. Okay, it is just inside the region of magnetic field. The positive charge is just inside the region of magnetic field. I am throwing it with a velocity v, as I have shown, and qbd is less than mv. This condition is given that qbd is less than mv, the significance of which you will understand later. Or I can say v is greater than qbd by m. I could have given it like that also. Let me give it like that. The speed with which the charge is thrown is greater than QB d by M. So let me put it that way. V greater than QB d by M. We will see the significance of this soon. So it is given a velocity which is more than QB d by M. So obviously this means that QB d by M should have dimensions of velocity. You will check it later. Question is, find angle of deviation of charge. Find angle of deviation of charge. Okay, I'll also give its mass M by the time it comes out of magnetic field. By the time it comes out of magnetic field region. So you have to find angle of deviation. Very interesting question. So let us analyze this. First of all, when the situation is given, first you find what is the angle between velocity and magnetic field. Velocity is on the plane of the board, magnetic field is into the plane. So angle between velocity and magnetic field is 90. So the path taken by this charge has to be circle. Because it's a positive charge, V cross B gives direction of center and force should be along center. If you do V cross B, V is to the right, B is in. Okay, do V cross B, it is along this line. It is along this line. Now, should I put the center within the region of magnetic field or outside the region of magnetic field? That's the question. If center is within the region of magnetic field, radius should be less than d. Can you see that? Less than the width of magnetic field. But if center is outside the region of magnetic field, radius should be more than d. Now, radius is mv by qb. mv by qb. Is it more than d or less than d? You check from here. This condition is given. So, mv by qb is more than d. Means center should be here. This is the center. With that center, if you try to draw a circle, it will look like that. And by the time it comes out of magnetic field, from there it will go in a straight path. Speed remains same because magnetic field never changes speed. So it was supposed to go straight like that, but due to magnetic field it turned. So it was supposed to go straight like this. So this angle is the angle of deviation which I have to find. Now how do I find it? You join that point to center. This angle is 90. So this is 90 minus theta, but this is 90. So this has to be theta. This is r, and this length is r minus d. Can you see that? So what is cos theta from the diagram? Cos theta is r minus d by r. That is 1 minus d by r. R is mv by qb. And this is the angle of deviation. So directly one step I am getting. So angle of deviation in this case is theta is cos inverse or arc cos 1 minus qbd by mv. This is the answer. So we have at least now some idea of this circular motion. Okay, so of the three paths possible in a uniform and steady magnetic field, of three paths possible, one is a straight line, we have studied that, one is a circle. So we are left with the helical path, which we will do in our next class.